Ever pondered how businesses optimize their resources? Today we dive into the fascinating world of linear programming. This mathematical technique, my friends, is a secret weapon for optimization. It's like a puzzle solver for businesses, helping them maximize or minimize certain factors, all while staying within a defined set of rules. Sounds intriguing, doesn't it? Imagine a world where every decision, every strategy is subject to a set of constraints, and you're looking for the best possible outcome within those limitations. That's precisely what linear programming does. It brings clarity and precision to decision-making, especially when resources are scarce. From supply chain management to finance, from production planning to operations research, linear programming is a game changer. It's about making the most of what you've got and doing it in the most efficient way possible. So, ready to unravel the components of linear programming? Let's begin. The journey of linear programming starts with the objective function. Think of it as the destination of our mathematical journey. It's a linear equation that represents what we want to maximize or minimize. For instance, if we're trying to maximize profits, our objective function might be expressed as the sum of decision variables, each representing a product multiplied by their respective profits. Objective function sets the goal, but how do we reach it? It's time to meet our decision variables. Decision variables are the key players in our optimization process. These are the quantities we seek to determine. Think of them as the unknowns in our mathematical equation, the values we're trying to solve for. For instance, if you're a manufacturer, a decision variable might represent the number of units of a certain product you produce. These variables are at the heart of the problem, and their optimal values are what we're after. With decision variables in place, we now need some rules to play by. Enter constraints. Constraints are the boundaries, the rules of our game. They're the parameters that limit the values our decision variables can take, keeping our solutions realistic and feasible. Think of them as the walls within which our solutions must exist. For example, if we're manufacturing a product, a constraint could be the maximum number of units we can produce in a day. These constraints, these rules form our playfield, shaping the limits of our choices. Constraints define our playfield, the feasible region. The feasible region is our playground where we find our champion, the optimal solution. Picture this region as a realm of possibilities, a space where all the values our decision variables can take live harmoniously, aligning perfectly with our constraints. The feasible region, in essence, is a compilation of every plausible answer to our problem. Now, onto the star of our show, the optimal solution. This is the point within our feasible region that either maximizes or minimizes our objective function. It's the best possible answer we can find within our constraints. In a two-dimensional world, this optimal solution is usually found at a vertex or corner of our feasible region. So, we've identified our playground and we've pinpointed our champion, but remember, the world of linear programming is vast and filled with complexities. Found the optimal solution? Great. But the journey doesn't end here. Ready to go beyond? Let's explore corner point principle, simplex method, duality, and sensitivity analysis. First up, the corner point principle. This principle states that the optimal solution to any linear programming problem will occur at a corner or vertex of the feasible region. This is a fundamental concept that significantly simplifies finding optimal solutions. Next is the simplex method, an algorithm that systematically navigates the vertices of the feasible region to find the optimal solution. By moving from corner to corner, the simplex method ensures we reach the best possible result. Now, let's discuss duality. For every linear programming problem, there's a corresponding dual problem. This isn't just a shadowy twin. It provides valuable insights into the original problem. For instance, it can offer bounds on the optimal solution and is a powerful tool for sensitivity analysis. Speaking of which, sensitivity analysis is our final advanced concept. It's a technique used to understand how variations in the coefficients of the objective function and constraints can affect the optimal solution. It's like testing the waters of change without diving headfirst into the unknown. These advanced concepts enhance our understanding and application of linear programming. They're like a secret toolkit, helping us unlock the full potential of this mathematical technique for optimization. And remember, practice makes perfect. So go ahead, dive into the world of linear programming and start optimizing. linear programming, a powerful tool in the world of optimization. We've journeyed through its components, from objective functions and decision variables, to constraints, feasible regions, and optimal solutions. We've touched on more advanced concepts like the simplex method, duality, sensitivity analysis, and its vast applications. This mathematical technique truly offers a systematic way to make optimal decisions when resources are limited. Remember, every constraint is a new opportunity for optimization. That's all for today. Keep exploring, keep learning,